Hello, and welcome. I'm really glad you're here. Before we begin, take a quiet moment. If you enjoy calm science, slow storytelling, and learning something real as you drift towards sleep, consider subscribing. It helps this space grow, and it lets you return whenever you need a moment of calm curiosity. Now, let everything else fade. Somewhere in the universe, gravity becomes so strong that even light can no longer escape. No drama. No sound, just a boundary written into space and time. Tonight, you'll follow only what science can measure and observe. Slowly, clearly, gently, so soften your breathing and begin by grounding yourself in the one force that touches everything you know. Gravity. You begin by noticing gravity in the simplest possible way. Your body rests against the ground, supported without effort or thought. This quiet contact is not passive. It is the result of Earth's mass pulling every part of you inward. Gravity acts on all matter with mass everywhere all the time. You feel it constantly, even when you are unaware of it. Gravity was once described as a force that pulls objects toward one another. That description works well for everyday experience. When you drop an object, it falls toward the ground at a predictable rate. When you jump, you return downward just as reliably. Careful measurements show that this acceleration is the same for all objects, regardless of their mass, when air resistance is removed. This consistency has been tested repeatedly, from laboratory experiments to observations made on the moon. You widen your attention from your own body to the planet beneath you. Earth is not pulling objects downward because it wants to, but because mass influences how objects move through space. The more mass something has, the stronger its gravitational influence becomes. Earth's mass is large enough to hold the atmosphere in place, to shape the flow of oceans, and to keep the moon bound in orbit. These effects are measured precisely through observation and calculation. You notice that gravity does not weaken or strengthen at random. This behavior follows clear mathematical rules. The gravitational attraction between two objects depends on their masses and the distance between them. When distance increases, gravitational influence decreases in a predictable way. This relationship was first described quantitatively by Isaac Newton, whose equations remain accurate for most everyday and planetary situations. Space missions still rely on these calculations to navigate spacecraft with extraordinary precision. You let your mind drift outward to the motion of planets around the sun. Each planet follows a stable path called an orbit, shaped by gravity. These paths are not accidental. They are the natural result of forward motion balanced by gravitational pull. Observations of planetary positions, made over centuries, confirm that these orbits remain remarkably consistent. Small variations can be measured and explained, often caused by the gravitational influence of other planets. You notice that gravity acts across empty space. No physical connection is required. The sun's mass shapes the motion of planets millions of kilometers away. This influence travels without delay in the equations used for most practical purposes, though deeper understanding reveals more subtle behavior. What matters here is that gravity does not fade simply because space appears empty. It remains active wherever mass exists. You consider falling again, but now from a broader perspective. An object falling toward Earth is not being pulled through space in a straight line. Instead, its motion reflects the structure of space itself. Even before modern theories refined this idea, careful observation showed that motion under gravity follows smooth, predictable paths. These paths can be measured, calculated, and tested against reality with confidence. You turn your attention to the moon. Its presence offers one of the clearest demonstrations of gravity's reach. The moon remains bound to Earth, not because it is fixed in place, but because its forward motion balances Earth's gravitational pull. Laser measurements, reflected from mirrors placed on the moon's surface, confirm the moon's gradual drift away from Earth at a rate of a few centimeters per year. Gravity's influence is steady, measurable, and precise. You expand further toward the stars. Binary star systems provide another powerful confirmation. Two stars can orbit each other, locked in a gravitational relationship that reveals their masses and distances. By observing their motion, astronomers calculate properties that cannot be measured directly. These calculations consistently match predictions based on gravitational theory, reinforcing its reliability across vast distances. You notice that gravity does not depend on composition. A rock, a drop of water, and a piece of metal all respond to gravity in the same way when mass and distance are equal. This principle, tested with extreme precision, is known as the equivalence of gravitational and inertial mass. Experiments confirm this equality to extraordinary accuracy, supporting the foundations of modern gravitational theory. You rest with the idea that gravity shapes structure on every scale. It gathers dust into planets, gas into stars, and stars into galaxies. Observations of rotating galaxies reveal motions that require significant gravitational influence, even when visible matter alone is not enough to explain it. While additional factors are studied to account for these motions, gravity itself remains the organizing principle. You return gently to where you began, to your body supported by Earth. The same rules that guide galaxies also guide your quiet stillness. Gravity does not switch behavior between scales. It remains consistent, reliable, and deeply woven into the universe's structure. As mass increases and distances shrink, gravity's effects become stronger, preparing the ground for situations where space and time themselves respond more dramatically. You remain calm with this knowledge, aware that gravity is not mysterious in its presence, only in its extremes. What you understand here forms a stable base. From this foundation, it becomes possible to explore how gravity behaves when mass grows immense and distances grow small, and how the universe reveals these effects through careful observation. You allow your breathing to slow as these ideas settle. Gravity does not rush, and neither does understanding it. Instruments on Earth and in orbit continue to measure its influence with increasing sensitivity. Satellites rely on gravitational calculations to remain in stable paths, correcting their motion based on tiny variations predicted in advance. Even small discrepancies are investigated carefully, refining knowledge rather than overturning it. You notice that gravity also reveals itself through absence. Regions where mass is concentrated can be inferred from motion alone. This is how unseen companions of stars are discovered and how distant structures are mapped. Gravity leaves a measurable imprint, even when light does not. You stay with this quiet certainty. Gravity is universal, impartial, and constant in its rules. It does not require belief, only measurement. As conditions change, as mass grows and space responds, gravity continues to follow the same principles, guiding matter into ever more intense arrangements. In those arrangements, boundaries emerge where motion, light, and time behave in unfamiliar yet precisely describable ways under gravity, measured through patient observation. You settle into the idea that space and time are not separate backgrounds where events happen. They are part of the physical universe, shaped and measured just like matter and energy. This understanding grows from careful observation, not imagination. Experiments and precise measurements show that clocks, rulers, and motion respond to gravity in consistent ways. These responses reveal that space and time are connected. You begin with time, something you experience constantly. Time passes at a steady rate for you here on Earth, measured by vibrations of atoms inside clocks. These atomic clocks are among the most accurate instruments ever built. When identical clocks are placed in different gravitational conditions, they do not agree perfectly. This difference is small but measurable. It confirms that gravity affects the flow of time itself. You notice that clocks placed higher above Earth tick slightly faster than clocks closer to the surface. This effect has been measured repeatedly using satellites and ground-based instruments. Global positioning systems must correct for this difference to function accurately. Without accounting for gravitational time dilation, navigation errors would grow quickly. These corrections are not optional adjustments. They are required by observation. You turn your attention to space. Distances are measured using rulers, radar signals, and light travel time. When mass is present, these measurements shift subtly. Light passing near massive objects bends from its straight-line path. This bending has been observed during solar eclipses and through modern telescopes. The amount of bending matches predictions with remarkable accuracy. You begin to understand gravity not as a force pulling across empty space, but as the result of curved spacetime. Mass and energy change the geometry around them. Objects move along the straightest possible paths within that geometry. These paths appear curved when viewed from a distance. This description replaces the idea of gravity as a mysterious pull with a clear geometric framework. You stay grounded in evidence. Mercury's orbit does not follow Newton's predictions exactly. Its closest approach to the Sun shifts slightly over time. This shift was measured carefully and could not be explained by other planets alone. The curvature of spacetime around the Sun accounts for the difference precisely. This agreement strengthens confidence in the theory. You notice that spacetime curvature is usually gentle. Earth's mass produces small effects that require sensitive instruments to detect. You do not feel time slowing or space bending because the changes are tiny. Yet they are real, measurable, and consistent. When mass increases or distances shrink, these effects grow stronger. You consider free fall. When you fall freely, you feel weightless, even though gravity is still present. Experiments show that objects in free fall follow the natural paths of spacetime. This is why astronauts in orbit experience weightlessness. They are not beyond gravity. They are moving along curved spacetime without resistance. You rest with the idea that motion and gravity are deeply linked. Accelerating frames and gravitational fields produce similar effects. This equivalence has been tested with increasing precision. It explains why gravity affects light, time, and motion together. Spacetime provides a single structure that connects these behaviors. You widen your view to stars and galaxies. Massive objects create deeper curvature. Light from distant stars bends around galaxies, forming arcs and multiple images. These patterns are observed and mapped. They allow astronomers to calculate mass distributions that would otherwise remain hidden. The results align with predictions from curved spacetime. You remain calm as the universe feels more structured, not more mysterious. Space and time respond predictably to mass and energy. Equations describe this relationship, but the underlying idea remains simple. Geometry replaces force. Motion follows shape. You allow this understanding to settle gently. Space and time are active participants in the universe, not passive containers. Their behavior is revealed through clocks, light, and motion. As mass grows denser, curvature deepens. In those regions, the familiar flow of time and the straightness of paths begin to change more noticeably. You think again about measurement because science rests on measurement. Spacetime curvature is not inferred from a single observation, but from many independent lines of evidence. Radar signals sent to planets take slightly longer paths when passing near the Sun. This delay has been measured with spacecraft and matches theoretical values. Each confirmation adds stability to the picture. You consider how gravity affects energy. Light climbing out of a gravitational field loses energy and shifts to longer wavelengths. This gravitational redshift has been observed in laboratories and astronomical settings. Even on Earth, photons moving upward experience this shift, detectable with sensitive equipment. The effect is small but real. You reflect on how this understanding changes perspective. Space and time are not fixed stages. They evolve with the distribution of mass and energy. This evolution is slow and orderly in most places. Only in extreme environments do the effects become dramatic. Yet the same rules apply everywhere. You return briefly to Earth-based experiments. Towers, airplanes, and satellites carry clocks to different heights. Their readings are compared after careful synchronization. The results consistently show time flowing at different rates depending on gravitational potential. These experiments remove doubt. The universe behaves as described. You notice how calm this knowledge feels. Nothing here violates intuition once it is understood. Spacetime curvature does not require belief, only acceptance of evidence. It replaces older ideas not because they were wrong, but because they were incomplete. You stay with the idea that motion follows geometry. Planets, light, and even time itself trace paths set by mass. This view prepares the mind for environments where curvature grows strong. In those places, familiar expectations must adjust, guided not by imagination, but by the same measured principles. You remain steady as these ideas settle into awareness. Spacetime is not something you leave behind when you look outward. It is present here, shaping every motion quietly. The ground beneath you, the satellites above, and the light reaching your eyes all follow its structure. As mass increases and space grows more tightly curved, the effects that are subtle here become clearer. Time slows, paths bend more strongly, and escape becomes harder. These changes are not sudden or magical. They emerge smoothly from the same relationships already measured and confirmed, waiting patiently wherever gravity gathers enough strength. You rest with the certainty that understanding grows from continuity. The universe does not switch rules. It deepens them. Where curvature intensifies, consequences unfold naturally, revealing boundaries defined not by matter, but by the behavior of space, time, and light. These boundaries remain invisible yet precisely defined, inviting careful observation rather than speculation through calm measurement and patient scientific attention always. You begin by turning your attention away from Earth and toward the stars scattered across the night sky. Each point of light represents a massive object held together by gravity, shining because of processes that can be measured and understood. Stars are not static. They are born, they change, and they eventually reach an end shaped primarily by their mass. You start with how stars form. Large clouds of gas and dust exist throughout galaxies. These clouds are observed using radio and infrared telescopes, revealing regions where material slowly gathers. Gravity causes denser regions within these clouds to contract. As they collapse, temperature and pressure increase. This process is gradual and governed by well-tested physical laws. When the central region becomes hot and dense enough, nuclear fusion begins. Hydrogen nuclei combine to form helium, releasing energy in the process. This energy moves outward as radiation and heat. At the same time, gravity pulls inward. The balance between outward pressure from fusion and inward gravitational pull creates stability. This balance is called hydrostatic equilibrium, and it defines most of a star's life. You notice that mass determines how this balance plays out. A star with relatively low mass, like the Sun, burns its fuel steadily over billions of years. A more massive star contains far more material, which increases gravitational pressure at its core. This pressure raises the temperature, causing fusion reactions to proceed faster. As a result, massive stars shine brighter but live shorter lives. You stay grounded in observation. Astronomers classify stars by mass, temperature, and brightness. These properties are plotted on diagrams that reveal clear patterns. Massive stars appear hotter and more luminous. Their spectra show elements undergoing fusion at higher energies. These measurements are not theoretical guesses. They are collected from light that travels across space and is analyzed with precision. You remain calm as you consider the pace of nuclear fusion. In massive stars, hydrogen is consumed rapidly. Once hydrogen in the core is depleted, fusion does not stop immediately. The core contracts under gravity, raising temperature further. This allows helium to fuse into heavier elements like carbon and oxygen. Each new fusion stage produces energy for a time, restoring balance briefly. You observe that fusion progresses in layers. In very massive stars, different elements fuse in shells surrounding the core. Hydrogen may still fuse in outer layers while heavier elements fuse deeper inside. This structure has been confirmed by models that match observed stellar behavior and by studying remnants of stellar explosions. You notice that each fusion stage lasts for a shorter time than the one before. Hydrogen fusion can last millions of years in massive stars, but later stages may last only thousands or even days. This acceleration happens because heavier elements release less energy when fused. Gravity continues to demand support, but fusion becomes less capable of providing it. You consider the role of energy loss. Stars radiate energy continuously into space. This radiation is measured as light across many wavelengths. To maintain balance, fusion must replace the lost energy. When fusion slows or stops, gravity gains the advantage. This competition is quiet and constant, never dramatic until balance is finally lost. You let this idea settle gently. A star does not collapse suddenly without cause. Its structure responds predictably to changing conditions in its core. Each stage follows from the last. Mass sets the scale of everything that follows, from temperature to lifespan to final outcome. You turn to observational evidence of aging stars. Astronomers identify stars at different stages by their color and brightness. Red supergiants represent a late stage in massive stellar evolution. Their outer layers expand while the core contracts. These stars are observed directly, and their properties match theoretical expectations. You remain focused on the calm rhythm of stellar change. Even in massive stars, most of life passes in relative stability. The dramatic end occupies only a small fraction of total time. What matters is the long buildup, driven by mass and governed by gravity and nuclear physics. You think about the elements around you. Many were formed in stars through fusion. Spectroscopic analysis shows that heavier elements are present in stellar atmospheres and in interstellar space. This evidence confirms that stars are chemical engines, transforming simple elements into more complex ones over time. You stay aware that not all stars reach the same end. Lower mass stars shed outer layers gently and leave dense remnants. Massive stars follow a different path. Their cores grow heavier as fusion proceeds. Eventually, iron forms in the core. Iron fusion does not release energy. This marks a critical point. You rest with this understanding. Once iron dominates the core, fusion can no longer support the star against gravity. The balance that defined the star's life begins to fail. This failure is not sudden or mysterious. It follows directly from measurable properties of nuclear reactions and mass. You slow your breathing as these facts settle. Massive stars live fast, bright lives shaped by their weight. Their internal processes are inferred from light, motion, and elemental signatures. Every conclusion rests on observation tested against theory. You remain calm as the idea of collapse approaches, not as drama, but as inevitability. Gravity has always been present, held in check by fusion. When fusion can no longer respond, gravity continues alone. This transition marks a turning point where structure gives way to compression. You stay with the quiet certainty that nothing here is speculative. The life cycle of massive stars is reconstructed from many independent observations. Their beginnings, changes, and endings align with physical laws measured on Earth and applied across space. As mass concentrates further and nuclear support fades, gravity begins to dominate in a way that leads inward, toward conditions where familiar forms of matter can no longer maintain stability under their own weight. You remain with the quiet moment when nuclear fusion no longer provides support. Inside the core of a massive star, energy production slows as iron accumulates. Iron nuclei do not release energy when fused. This is not a flaw in the process, but a well-measured property of nuclear physics. Without outward energy pressure, gravity continues inward without resistance. You focus on the core itself. Its mass is immense, packed into a region no larger than a city. Temperature remains extremely high, yet temperature alone cannot stop collapse. Gravity compresses matter further, forcing electrons closer to atomic nuclei. At this stage, ordinary atomic structure begins to fail under pressure. You notice that electrons are governed by quantum rules. They resist being forced into the same state, creating a pressure known as electron degeneracy pressure. This pressure is not related to heat. It arises from the fundamental behavior of particles. In less massive stars, this pressure can halt collapse, forming dense objects such as white dwarfs. Observations of white dwarfs confirm their predicted sizes and masses. In more massive cores, even electron degeneracy pressure is not enough. Gravity overwhelms it. Electrons are pushed into protons, forming neutrons and releasing neutrinos. This process is observed indirectly through sudden bursts of neutrinos detected on Earth from distant stellar collapses. These detections confirm that core compression proceeds rapidly and violently, even though the process itself remains hidden from direct view. You remain calm as you consider neutron matter. Neutrons also resist compression due to quantum effects. Neutron degeneracy pressure can halt collapse in some cases, creating neutron stars. These objects are observed as pulsars, emitting regular radio signals that reveal their mass, size, and rotation. Measurements confirm their extreme density, matching predictions precisely. You stay focused on the fact that not all collapsing cores stop there. When the core's mass exceeds a critical threshold, neutron pressure also fails. This limit is calculated from known physical laws and supported by observation. Beyond it, no known force can counter gravity. Collapse continues inward without pause. You think about timescales. The core collapse itself happens in less than a second. This is inferred from neutrino detections and changes in emitted radiation. While the outer layers of the star may take longer to respond, the central collapse is swift. Gravity does not hesitate once resistance disappears. You observe that this collapse is not chaotic. It follows strict physical rules. Matter accelerates inward, densities rise beyond those found in atomic nuclei, and spacetime curvature increases sharply. These conditions cannot be recreated fully in laboratories, but they are constrained by theory and observation together. You notice that pressure, temperature, and density lose their familiar meanings. Matter behaves collectively rather than as individual atoms. Models based on quantum mechanics and relativity describe this behavior consistently. While details remain under study, the overall process is well supported by evidence. You return to observation again. Supernova remnants show elements formed during collapse and explosion. Their distribution and composition match predictions. Pulsars spin at rates that reflect conservation of angular momentum during collapse. Everything points to an inward compression governed by gravity alone. You remain steady as the idea deepens. Gravity does not become stronger in a mystical sense. Its influence simply becomes dominant when all opposing pressures fail. This dominance is not sudden or surprising. It is the natural result of increasing mass and decreasing volume. You consider how little space remains inside the core. Distances shrink. Matter packs tighter. Light struggles to escape the growing curvature of spacetime. These effects are predicted mathematically and supported by indirect measurements. Nothing here contradicts known physics. You allow yourself to rest in the certainty that collapse is not destruction, but transformation. The star's core enters a new regime defined by gravity. Known forces step aside, not because they vanish, but because they are insufficient. Gravity continues inward, shaping what follows. You stay calm as the boundary between supported matter and unstoppable collapse approaches. This boundary is defined by mass, pressure, and geometry, not by uncertainty. It marks the point where spacetime itself begins to respond more dramatically to concentrated mass. You slow your breathing as the universe grows quieter. Inside the collapsing core, events unfold beyond direct observation, yet remain constrained by measurable laws. The equations guiding this process have been tested wherever possible, and they remain consistent. You remain aware that collapse does not announce itself loudly. It proceeds according to balance lost and gravity unopposed. The result is not an object yet, but a region where ordinary descriptions fail. As matter continues inward beyond all known resistance, gravity defines a boundary where escape becomes impossible, not because of force alone, but because spacetime itself bends inward without return. You remain with the inward motion of matter as collapse continues without resistance. The core's mass is now confined to an extraordinarily small region. Density rises beyond the limits where atomic nuclei can remain distinct. At this stage, gravity no longer acts only on matter, but strongly reshapes the surrounding structure of space and time. You notice that a black hole does not form as an object in the usual sense. There is no surface, no solid boundary, and no central body that can be touched or seen. Instead, a black hole is defined by its gravitational influence. It is a region where mass has been compressed so tightly that spacetime becomes deeply curved inward. You focus on what determines this transition. When a collapsing core passes a critical radius for its mass, escape becomes impossible. This radius is calculated precisely from general relativity. It depends only on mass and fundamental constants. This calculation has been tested repeatedly and matches observations of compact objects throughout the universe. You remain grounded in evidence. Black holes are not inferred from darkness alone. They reveal themselves through motion. Stars orbit invisible companions with masses too large to be neutron stars. Their speeds and paths can be measured accurately. These measurements show gravitational effects that only a black hole can produce. You observe how gas behaves near these regions. As matter falls inward, it heats up through friction and compression. This hot gas emits X-rays before disappearing from view. X-ray telescopes detect these emissions from systems where a visible star feeds material into an unseen companion. The energy and variability of the radiation match predictions precisely. You consider how mass settles into its final configuration. The collapsing matter does not remain chaotic. It radiates energy and angular momentum until it reaches a stable state. The resulting black hole is described completely by mass, rotation, and electric charge. This simplicity is not assumed. It is derived from solutions to Einstein's equations and supported by observation. You remain calm as the idea becomes clearer. The matter that formed the black hole does not continue behaving as ordinary matter. Its detailed structure becomes inaccessible to outside observers. What remains observable is the gravitational field it creates. This field shapes the motion of nearby matter and light. You notice that black holes do not consume their surroundings indiscriminately. Objects must approach closely to be affected strongly. From a distance, a black hole's gravity behaves like that of any other object with the same mass. Planets could orbit a black hole just as they orbit stars, provided they remain far enough away. You return to the moment of formation. As collapse completes, an invisible boundary forms around the mass. Beyond this boundary, paths through spacetime lead inward only. This boundary is not material, yet it has measurable properties. Its size depends on mass and can be calculated exactly. You stay with the evidence again. Gravitational waves detected on Earth reveal the merging of black holes. These waves carry information about mass and rotation. The signals match predictions with extraordinary accuracy. They confirm that black holes form, persist, and interact exactly as theory describes. You allow your breathing to slow as the universe feels orderly. Black holes are not violations of physics. They are solutions to well-tested equations under extreme conditions. Every observation so far aligns with these solutions. You think about how black holes grow. They gain mass by absorbing matter and merging with others. This growth is gradual and observable through changes in surrounding motion and radiation. Supermassive black holes at galaxy centers reveal their presence by influencing stellar orbits over vast distances. You remain steady as the idea of invisibility settles. A black hole cannot be seen directly because light cannot escape from within its boundary. Yet its presence is unmistakable through its effects. This invisibility is not mysterious. It follows directly from the behavior of light in curved spacetime. You rest with the knowledge that black holes are common. Stellar remnants, galactic centers, and distant mergers all point to their widespread existence. Their formation is a natural outcome of gravity acting on sufficient mass. You stay calm as complexity gives way to clarity. Nothing supernatural occurs at formation. Known laws operate without interruption. Matter collapses, spacetime curves, and a stable gravitational region emerges. You reflect on how careful measurement replaces fear with understanding. Black holes do not erase physics. They challenge it to operate at its limits. Those limits are approached carefully, guided by observation rather than imagination. You remain aware that while the interior cannot be described fully with current knowledge, the boundary itself is defined precisely. Its properties can be calculated, measured indirectly, and confirmed repeatedly. As mass settles into this final state, gravity creates a quiet region where paths converge inward, and light itself traces curves that no longer lead back out, marking the formation of a boundary defined purely by space-time geometry. You settle into the idea that a black hole is defined by a boundary, not by a surface you could touch. This boundary is called the event horizon, and it is described with precision rather than imagery. It exists because gravity affects how motion and light behave when mass becomes extremely concentrated. The event horizon marks the distance from the center where escape is no longer possible. You begin with escape velocity, a concept measured and tested long before black holes were understood. Escape velocity is the speed an object must reach to move away from a massive body without falling back. On Earth, this speed is high but achievable with rockets. The value depends on Earth's mass and radius, both of which are measured accurately. You imagine increasing mass while keeping it confined to a smaller region. As mass increases or radius decreases, escape velocity rises. This relationship is straightforward and calculable. At a certain point, escape velocity reaches the speed of light. This speed is not arbitrary. It is a universal constant measured in laboratories and confirmed through countless experiments. You pause with this fact. Light always travels at the same speed in a vacuum. Cannot move faster. When escape velocity equals this speed, even light cannot move outward. This defines the event horizon. It is not a wall or barrier. It is a location in spacetime where all possible outward paths curve back inward. You remain grounded in measurement. The radius of the event horizon depends only on mass. This radius can be calculated exactly using equations from general relativity. For Earth's mass, this radius would be smaller than an atom. For the Sun's mass, it would be only a few kilometers. These values are precise and consistent. You notice that nothing special happens to space far away from this boundary. Gravity weakens with distance as usual. An observer far from the black hole cannot detect the horizon directly. Its presence is inferred through motion, light behavior, and timing effects near the boundary. You think about how light behaves as it approaches this region. Light emitted outward from near the horizon loses energy as it climbs through curved spacetime. Its wavelength stretches, shifting toward red. This gravitational redshift has been measured near dense objects and matches theoretical predictions closely. You remain calm as the idea settles. The event horizon is not a place where matter is crushed or destroyed instantly. It is simply where outward paths no longer exist. Objects crossing it continue inward because spacetime itself leads that way. You consider the experience of a distant observer. From far away, signals from an infalling object appear to slow and fade. This effect arises from time dilation, which has been measured in weaker gravitational fields and confirmed repeatedly. The fading is not illusion. It reflects how time and light behave near strong gravity. You notice that the horizon itself does not emit light. It has no texture, temperature, or structure that can be observed directly. Its properties are defined mathematically and confirmed indirectly. This makes it different from ordinary boundaries, yet no less real. You return to evidence. The size of black holes measured through stellar orbits matches predicted horizon sizes. In some systems, gas motion reveals inner edges consistent with calculated event horizon locations. These observations do not rely on assumption. They rely on repeated measurement. You remain steady as the universe feels orderly again. The event horizon is not mysterious once its definition is understood. It arises naturally from the relationship between mass, distance, and the speed of light. No new physics is required to define it. You think about how rotation affects this boundary. Spinning black holes have horizons shaped slightly differently, predicted by equations and supported by observation. These effects influence how matter and light behave nearby. Even then, the boundary remains well defined. You stay aware that the event horizon does not pull things inward by itself. Gravity does not suddenly increase at that location. The change is geometric. Paths that once allowed escape simply no longer do. You allow this understanding to rest gently. The event horizon is not a cliff or doorway. It is a limit set by spacetime structure. This structure has been mapped carefully through theory tested against observation. You breathe slowly as these ideas settle. The universe does not hide its rules. It reveals them patiently, through light, motion, and time. The event horizon stands as one of those rules made visible through consequence rather than substance. As gravity curves spacetime ever more strongly, light itself traces paths that spiral inward, revealing a boundary defined not by matter, but by the geometry that determines whether anything can ever return outward again. You focus your attention on light, something that usually feels simple and dependable. Light moves at a constant speed in a vacuum, a value measured so precisely that it defines modern units of distance. This constancy holds everywhere, even near extreme gravity. What changes is not light's speed, but the paths it is allowed to follow through curved spacetime. You begin by recalling that light normally travels in straight lines. This is true only when spacetime itself is flat. When mass is present, spacetime curves, and light follows the straightest possible paths within that curved geometry. These paths appear bent to an outside observer. This bending is not hypothetical. It is observed whenever light passes near massive objects. You consider how this effect grows stronger near a black hole. The curvature of spacetime increases as distance to the mass decreases. Light approaching closely no longer follows gentle arcs. This path bends sharply inward. At specific distances, this bending becomes so strong that light can circle the black hole before either escaping or falling inward. You stay grounded in calculation. General relativity predicts a region where photons can orbit in unstable paths. These orbits are not like planetary orbits. They require exact conditions and cannot persist indefinitely. Small disturbances cause the light to spiral inward or outward. This region has a precisely defined radius based on the black hole's mass. You note that this prediction is supported by observation. The dark silhouette seen in images of black holes is not the event horizon itself, but a shadow formed by light paths that fall inward. Light that might have reached the observer is redirected or captured. The size and shape of this shadow match theoretical predictions with remarkable accuracy. You remain calm as you consider what happens closer in. As light moves outward from deep gravitational regions, it loses energy. Its wavelength stretches, shifting toward longer wavelengths. This gravitational redshift has been measured near dense stars and galaxies. Near a black hole, the effect becomes extreme. You pause with the idea that light emitted exactly at the event horizon cannot escape. Its outward path curves back inward, not because light slows down, but because spacetime itself tilts inward. There is no direction that leads away. This defines the point of no return with precision rather than drama. You think about how this affects information. Light carries information about where it came from. Once light cannot escape, information cannot either. This is not a philosophical statement. It is a physical consequence of how signals move. Observations confirm that no radiation emerges from within the boundary. You consider how this is observed indirectly. Matter falling toward a black hole emits radiation until it crosses the horizon. Beyond that point, emissions cease. Telescopes detect sharp inner edges in accretion disks, consistent with predicted boundaries. These observations repeat across many systems. You stay aware that nothing special happens to light exactly at the boundary from its own perspective. According to theory, light continues to move locally at its usual speed. The change is global, not local. Paths that once connected outward no longer do. You return briefly to gravitational lensing. Light from distant stars bends around black holes, producing rings and arcs. These distortions are measured precisely. They allow astronomers to map mass and confirm spacetime curvature. The results align with predictions without adjustment. You remain steady as the behavior of light reveals the structure of gravity. Light is not trapped by force. It is guided by geometry. This distinction matters because it keeps the explanation grounded in measurement rather than imagery. You reflect on how calm this understanding feels. Even in extreme conditions, physics remains consistent. Light does not behave unpredictably. It follows rules that have been tested wherever possible. You notice that rotation adds complexity. In rotating black holes, spacetime itself is dragged along. Light paths twist accordingly. These effects are predicted and supported by observation of nearby matter and radiation patterns. You allow the idea of no return to settle gently. It is not a sudden barrier. It is the point where all future directed paths lead inward. This definition is precise, mathematical, and supported by evidence. You breathe slowly as these facts rest in your awareness. Light reveals what matter cannot. By tracing its paths, the universe makes invisible boundaries observable. As curvature deepens and light's possible routes narrow, a quiet limit emerges where outward motion no longer exists, defined not by darkness, but by the way spacetime itself closes every path that once led away. You turn your attention to time, something that usually feels steady and uniform. Seconds pass, breaths rise and fall, and clocks mark each moment with quiet regularity. Yet careful measurement shows that time does not flow at the same rate everywhere. Gravity influences time in ways that are subtle near Earth and extreme near dense objects. You begin with what can be measured directly. Atomic clocks placed at different heights above Earth do not remain synchronized. Clocks closer to Earth's surface tick slightly more slowly than those farther away. This difference has been measured repeatedly using towers, aircraft, and satellites. The effect is small, but it is real, consistent, and predictable. You rest with the idea that gravity affects time itself. This is not a mechanical delay or a signal error. It is a change in how time passes locally. The stronger the gravitational field, the slower time flows relative to regions with weaker gravity. This relationship is described precisely by general relativity and confirmed through observation. You expand your view toward more massive objects. Near stars denser than the Sun, time dilation becomes stronger. Light escaping these regions shifts toward longer wavelengths, carrying evidence of slower clock rates below. These shifts are measured in stellar spectra and match predictions without adjustment. You move closer in your understanding toward the region near a black hole. As gravity strengthens, the difference in time flow becomes more pronounced. A clock held near the event horizon would tick far more slowly compared to one far away. This slowing is not imagined. It follows directly from equations that have been tested in weaker fields. You consider how this appears to a distant observer. Signals sent outward from near the black hole take longer to arrive. Each signal is stretched in time, arriving more slowly than the one before. This effect has a clear cause. Time near the source flows more slowly relative to the observer. You stay grounded in physics. From the perspective of the clock near the horizon, nothing unusual happens locally. Seconds still feel like seconds. Processes unfold normally. The difference arises only when comparing measurements between regions with different gravitational strengths. You notice that this relativity of time has no contradiction. Both perspectives are valid within their own frames. This principle has been tested through experiments involving relative motion and gravity. It remains consistent across all observations. You pause with the idea that time dilation increases smoothly. There is no sudden jump or disruption at the event horizon. The slowing becomes more extreme as the boundary is approached. This gradual change reflects the smooth geometry of spacetime. You reflect on how this understanding removes confusion. Time does not stop in any absolute sense. It slows relative to distant observers. This distinction is critical and supported by mathematical description and experimental confirmation. You return briefly to technology. Satellites orbiting Earth experience both motion-related and gravity-related time dilation. Their onboard clocks are corrected continuously. Without these corrections, systems like GPS would fail quickly. This everyday dependence confirms that time dilation is not theoretical. You remain calm as you consider what happens at the boundary itself. From far away, the clock near the horizon appears to slow indefinitely. Signals fade and stretch. This does not mean the clock freezes. It means that light and time are increasingly distorted as signals climb out of deep curvature. You stay with the idea that time is part of spacetime, not an independent backdrop. Mass shapes spacetime. As curvature increases, time responds. This response is measured, calculated, and confirmed wherever observation allows. You consider how this affects matter falling inward. Chemical reactions, physical processes, and biological functions would proceed normally according to local time. Only when compared across gravitational differences does the disparity appear. You breathe slowly as this settles. Time remains reliable locally. Its variability emerges only through comparison. This preserves consistency while allowing flexibility across the universe. You notice that time dilation is not unique to black holes. It occurs near all massive objects. Black holes simply represent the extreme limit. They do not introduce new rules. They reveal the full consequence of existing ones. You remain steady as the universe feels orderly again. Time does not break. It bends. Its behavior follows geometry just as motion and light do. You reflect on observation once more. Although no clock can be held at the horizon indefinitely, the behavior of matter and radiation nearby confirms predicted effects. Accretion disk timing, signal delays, and redshift measurements all align with theory. You rest with the certainty that time is measurable, even when altered. Its changes are not mystical. They arise from mass, distance, and geometry. As gravity deepens and spacetime curves inward, time itself stretches and slows, revealing that even the flow of moments is shaped by mass, guiding events toward a boundary where comparison with the outside quietly fades. You begin by noticing that observation depends on where you stand and how you measure. Two people can watch the same event and record different details without either being wrong. This is not a flaw in physics, but a fundamental feature of spacetime. Gravity and motion affect clocks, distances, and light, so measurements vary with perspective. You are not asked to choose one view as more real. You are asked to understand how both fit together. You imagine a distant observer, far from the black hole, watching from a safe distance where gravity is weak. From this vantage, space appears nearly flat and time flows steadily. Light from the region near the black hole reaches the observer after traveling through curved spacetime. The observer measures signals that are delayed, stretched, and reddened. These effects are predictable and consistent with general relativity, because the geometry of spacetime determines how light travels. Now you imagine someone falling toward the black hole, carrying a clock and a flashlight. Locally, everything feels ordinary. The flashlight behaves as expected, and the clock ticks steadily. The falling person does not notice time slowing in their immediate surroundings. The physical laws they experience remain the same. Their path through spacetime follows the natural trajectory of freefall, which is the straightest possible line in curved geometry. The key difference lies in how each observer compares measurements. The distant observer sees the falling person's signals arrive more slowly over time. The signals become redder and weaker. This happens because each successive pulse must climb out of a deeper gravitational well, losing energy and taking longer to escape. The observer might infer that the falling person slows and freezes near the boundary, though the falling person does not experience any such freezing. This apparent contradiction is resolved when you remember they use different coordinates. You focus on the idea of frames of reference. Each observer uses their own local time and local distance to describe events. In relativity, there is no universal clock that applies to all observers. Instead, each measurement is tied to the observer's position and motion. This principle has been tested with atomic clocks in aircraft, satellites, and laboratories. The results consistently show that clocks in different conditions do not agree unless corrected for gravity and motion. You consider how this affects the concept of simultaneity. Two events that appear simultaneous to the distant observer may not be simultaneous for the falling person. The order of events can shift depending on the observer's frame. This is not arbitrary. It is a direct consequence of the geometry of spacetime, which has been confirmed through experiments involving fast-moving particles and precise timing systems. These results show that time is not absolute, and simultaneity is relative. You return to what the distant observer can measure. The observer can track the position of the falling person using light signals. Each measurement carries a delay. The observer must account for the time it takes light to travel. As the falling person approaches the boundary, the delay increases dramatically. The observer's measurements show the person approaching the boundary asymptotically, never quite reaching it within finite observer time. This is a result of the increasing gravitational time dilation. You also consider the falling person's measurements. They can measure local distances using rulers and local time with their clock. For them, the boundary is crossed in a finite amount of their own proper time. They do not see any special feature at the boundary itself. Their experience is continuous. This difference in experience is not a contradiction but a demonstration of how spacetime allows multiple valid descriptions. You notice that what counts as a when depends on how you slice spacetime into layers of constant time. You remain grounded in evidence. The behavior of clocks in different gravitational fields is not hypothetical. It is measured in systems like GPS, where corrections for both gravity and motion are essential. Without these corrections, positional errors would accumulate rapidly. The system's continued accuracy confirms that time dilation is real and must be accounted for in practical technology. You consider how signals from the falling person would appear if the distant observer had a powerful telescope. The observer would see the person's image increasingly redshifted. Eventually, the light becomes so red that it falls out of the visible range. The person's image fades not because the person disappears, but because the signals reaching the observer carry less and less energy. This fading is a natural consequence of the way gravity affects light. You reflect on how this affects our understanding of what it means to see something. Observation is always limited by the signals that reach you. The distant observer cannot access information from inside the boundary because no signals can escape. This limitation is not due to equipment failure. It is a physical consequence of spacetime geometry. The boundary defines a region from which no information can reach the outside. You stay calm with the idea that physics remains consistent for both observers. Each description follows the same underlying laws. The difference lies in the coordinate systems used to describe events. General relativity provides a framework that translates between these systems, ensuring that physical predictions agree when properly interpreted. You think about how this principle extends beyond black holes. Even on Earth, observers in different gravitational potentials or moving at different speeds must account for relativity when comparing measurements. Particle accelerators, atomic clocks, and satellite systems all confirm that relativity is not a theoretical curiosity, but a practical reality. You breathe slowly as the idea settles. The universe does not force a single viewpoint. Instead, it allows multiple perspectives, each valid within its own frame. Understanding this helps you accept that the boundary is not a place of contradiction, but a place where spacetime geometry makes certain measurements impossible for outside observers. You remain aware that the falling person's experience and the distant observer's measurements are connected through light and time. The connection is not direct, because the boundary blocks signals. Yet the relationship is defined precisely by the same laws that govern every gravitational interaction. This connection keeps the description consistent, even when appearances differ. You rest with the calm certainty that observation depends on position, motion, and gravity. What you can measure is limited by the paths available to light and signals. In strong gravity, those paths narrow until they end, leaving only the outside view and the local experience, each complete and self-consistent, yet forever separated by the boundary that defines escape. Each perspective is a complete, honest story. You begin by noticing that black holes are not observed like ordinary objects. You cannot point a telescope at a black hole and see its surface. Instead, you observe what happens around it. Light, matter, and radiation respond to the black hole's gravity in ways that can be measured. These effects provide evidence that is as strong as direct observation, because the laws governing them are well understood and repeatedly confirmed. You start with the idea of a shadow. The black hole itself is invisible because light cannot escape from inside the boundary, but the region around it can glow brightly. Gas falling toward the black hole forms an accretion disk, a rotating structure heated by friction and compression. This hot gas emits light across many wavelengths, including radio waves and X-rays. The black hole's gravity bends the paths of this light, creating a visible contrast, a dark area surrounded by bright emission. You notice that the dark area is not the event horizon itself, but a shadow produced by light paths that fail to reach the observer. Light emitted from behind the black hole is bent around it, while light emitted from near the boundary can be captured. The result is a silhouette. The size and shape of this silhouette depend on mass and rotation, and they can be calculated precisely. You remain grounded in measurement. The Event Horizon Telescope, EHT, is a global array of radio telescopes that works together as a single instrument through a technique called very long baseline interferometry. This technique measures tiny differences in the arrival time of radio waves at different locations. The data is combined to create an image with resolution sufficient to reveal the shadow of a black hole. You think about how challenging this measurement is. The black hole's shadow is extremely small in angular size, even for the nearest supermassive black holes. Yet the EHT succeeded in capturing an image by observing at millimeter wavelengths and combining data from telescopes separated by thousands of kilometers. The resulting image shows a ring of emission surrounding a darker central region, consistent with theoretical predictions. You focus on what the image reveals. The ring's diameter corresponds to a size larger than the event horizon itself. This is expected because light can orbit the black hole at a radius larger than the horizon. The shadow appears larger due to the bending of light. The observed size matches predictions based on the mass estimated from other methods, such as stellar motion and gas dynamics. You remain calm as you consider how this evidence supports the theory. The shadow is not a simple black circle. Its shape and brightness distribution reflect the geometry of spacetime and the motion of gas. Simulations based on general relativity reproduce the observed patterns with high fidelity. This agreement is not trivial. It confirms that the behavior of light near strong gravity follows the predicted geometry. You turn your attention to other forms of evidence. Stellar orbits around the center of our galaxy reveal the presence of a massive, compact object. These orbits are measured using infrared telescopes that track the motion of stars over decades. The stars move in paths that can only be explained by a mass concentrated in a very small volume. The most straightforward explanation is a supermassive black hole. You consider the precision of these measurements. The orbits reveal the mass of the central object and its location. The mass is millions of times that of the Sun, yet it occupies a region no larger than our solar system. The density implied by these measurements is consistent with a black hole rather than any other known object. This conclusion is supported by repeated observation and careful modeling. You stay aware that black holes also reveal themselves through high-energy radiation. Gas falling into a black hole heats to extreme temperatures. The resulting X-rays are detected by space-based observatories. The variability of this radiation provides information about the size and dynamics of the inner region. These observations match models of accretion disks and relativistic effects near the boundary. You reflect on how these observations are linked to gravitational theory. The timing of variations in brightness reveals how fast gas orbits close to the black hole. These orbital speeds approach a significant fraction of the speed of light. Such speeds are predicted by general relativity for matter in strong gravity. The observed data aligns with these predictions, strengthening confidence in the model. You notice that evidence comes from multiple independent sources. Imaging, stellar motion, and radiation all point to the same conclusion. This convergence is a hallmark of strong scientific support. Each method has its own uncertainties, yet they agree within those limits. The agreement is not coincidental. It reflects the consistent behavior of gravity. You remain calm as you consider how the black hole's shadow connects to the event horizon. The shadow is a projection of the boundary's influence on light. It does not show the boundary itself, but it reveals its presence through the paths light takes. This indirect observation is powerful because it is grounded in measurable geometry. You return to the idea of a boundary defined by spacetime. The shadow provides a visual representation of how light behaves near strong gravity. It confirms that spacetime curvature is not only a theoretical concept but a measurable reality. The dark region is evidence that light paths are redirected or captured, consistent with a boundary where escape is impossible. You think about how this evidence affects understanding. The black hole is not an abstract prediction. It is a real object with measurable influence. The shadow is a reminder that the universe reveals its structure through light, even when light cannot escape from within. You breathe slowly as this settles. The shadow is not a mystical shape but a measurable consequence of known physics. It appears where light is forced to follow paths that cannot reach the observer. The result is a clear, repeatable pattern that confirms predictions. You remain aware that observation continues to improve. Future measurements will refine details, revealing more about rotation and gas behavior. Yet the core evidence remains stable. The shadow, the motion of stars, and the radiation from accretion all align with the predictions of strong gravity. You rest with the quiet certainty that even the invisible can be understood through its effects. The black hole's shadow is a boundary made visible through the bending of light, and it stands as a measured confirmation that spacetime curves exactly as theory describes, shaping what can be seen and what remains forever hidden. You begin by settling into the idea that information is a physical concept, not just an abstract one. In physics, information refers to the state of a system, the arrangement of particles, their energies, and their relationships. This state can be described mathematically, and changes to it follow precise laws. You can think of information as the set of details required to recreate a system's condition. It is not something mystical. It is a measurable property of physical systems. You notice that entropy is closely linked to information. Entropy is a measure of how many different ways a system can be arranged while appearing the same on a macroscopic level. A simple example is a gas in a container. If the gas molecules are spread evenly, there are many microscopic arrangements that look identical at larger scales. The entropy is high because the number of possible microstates is large. This concept is not merely theoretical. It is tested through thermodynamics and statistical mechanics, which predict behavior that matches experiments precisely. You reflect on the fact that entropy tends to increase in closed systems. This is not a rule that forbids local decreases. It is a statistical tendency that emerges from the large number of possible arrangements. The direction of increasing entropy is observed in many processes, from heat flowing from hot to cold to the mixing of substances. This observed trend gives time a direction, often called the arrow of time, because processes naturally move toward more probable, higher entropy states. You remain calm as you consider how black holes enter this discussion. Black holes appear to create a problem for information because anything that crosses the boundary can no longer send signals outward. From the perspective of an outside observer, information seems to vanish. This apparent loss challenges the idea that physical processes are reversible in principle. If information is lost, then the fundamental rules of physics would need revision. You think about how physicists respond to this challenge. One key insight is that black holes can be described by a small set of observable properties: mass, charge, and spin. This simplicity is supported by theory and observation. Yet it seems to erase the detailed information about what fell in. This is the source of the tension. The question is not whether the black hole exists, but whether the information about its contents is truly lost or simply inaccessible. You stay grounded in evidence. The idea that information is preserved is supported by the broader success of quantum mechanics. Quantum theory describes systems with precise probabilities and predicts outcomes that match experiments with extraordinary accuracy. A fundamental feature of quantum mechanics is that information is conserved in the evolution of closed systems. If black holes violate this, then either quantum mechanics or our understanding of gravity would require revision. You notice that this tension has led to careful theoretical work, not speculation. Physicists examine how information could be stored or encoded at the boundary, or how it might be released through subtle effects. These ideas are constrained by mathematical consistency and by what is already confirmed by observation. The work is not random. It is guided by the need to reconcile two well-tested frameworks: quantum mechanics and general relativity. You consider entropy again. Black holes have entropy too. This is not a metaphor. It is a property derived from theoretical work that connects gravity, thermodynamics, and quantum theory. The entropy of a black hole is proportional to the area of its boundary, measured in units defined by fundamental constants. This relationship has been tested indirectly through theoretical consistency and through how black holes behave when they interact with their environment. You remain calm as you think about temperature. Black holes have a temperature associated with them, which implies they emit radiation slowly. This emission is extremely weak for large black holes and is not directly observed in most cases. Yet the prediction is a logical consequence of combining quantum theory with curved spacetime. The emission provides a mechanism through which black holes can lose mass over long timescales. You focus on the implication. If black holes radiate, they can shrink. If they shrink, The information about what fell in cannot remain inside forever. This leads to questions about how that information is accounted for in the radiation. The details are still under study, but the question itself arises from applying well-tested principles consistently rather than from speculation. You return to measurement and limits. Even if information is preserved, the boundary limits what an outside observer can know. No signals can come from inside, so information remains inaccessible. This is not the same as loss. It is a limitation of observation. The difference matters because physics distinguishes between what is unknown and what is unknowable. You stay aware that many aspects of this topic remain active research areas. Yet the underlying principles remain clear. Physical laws are tested through observation, and any new theory must match existing evidence. The tension between gravity and quantum mechanics is not evidence of mystery, but evidence of an area where our current frameworks must be combined carefully. You breathe slowly as the idea settles. The universe does not allow information to disappear without consequence. The laws that govern particles and fields have proven reliable across countless experiments. This reliability guides physicists in resolving the apparent contradiction. You reflect on how this relates to entropy. The growth of entropy is observed everywhere, and black holes contribute to the overall accounting of entropy in the universe. When matter falls into a black hole, the entropy of the system changes in ways that can be described and calculated. This is not a poetic idea. It is a practical application of thermodynamics to a gravitational system. You remain calm with the understanding that limits in physics are not failures. They are signposts of where knowledge is constrained by observation. The event horizon is one such limit. It defines a region beyond which signals cannot escape. The boundary does not destroy physics. It defines where measurement ends. You rest with the quiet certainty that information, entropy, and limits are interconnected. They show how the universe maintains consistency even under extreme conditions. Gravity, quantum mechanics, and thermodynamics all apply. Their overlap points to areas where deeper understanding is required, but the need for coherence keeps the inquiry grounded. As you let your mind relax, you remain aware that the boundary itself is defined by geometry, not by mystery, and that the universe continues to reveal its rules through careful measurement, even when those rules approach the limits of what can be known. You begin by resting your awareness on a fact. Light takes time to travel. When you look at distant objects, you are not seeing them as they are now, but as they were when their light began its journey. This is a measured reality, confirmed by observations of galaxies, stars, and supernovae. The finite speed of light is a constant of nature, tested in many ways, and it defines the distance that can be observed in a given amount of time. Your mind follows the logic of this limit. The universe is about 13.8 billion years old, based on measurements of the cosmic microwave background, the expansion rate of space, and the distribution of matter. Because light travels at the speed, you cannot see objects whose light has not yet reached you. The farthest light we can observe has been traveling for nearly the age of the universe. This defines a boundary, not of the universe itself, but of what is observable from your location. You imagine the observable universe as a sphere centered on you, because you are the point from which light arrives. This does not imply you are special. Every observer has their own observable sphere. The universe may be much larger than what you can see, but the limit is unavoidable. It is set by the same physics that defines the boundary around a black hole, a region beyond which information cannot reach you. In one case, gravity prevents escape. In the other, time and light speed set the limit. You stay calm as you consider how this boundary is measured. Astronomers use redshift to determine distance. Redshift is the stretching of light waves as space expands. The more distant a galaxy is, the more its light is stretched, and the more its spectral lines shift toward longer wavelengths. This effect is measured using spectroscopy and provides a consistent map of distance and time. You follow the connection to cosmic expansion. Space is not static. It is expanding, and this expansion affects the distance that light must travel. The expansion rate is described by the Hubble constant, a value determined through multiple methods. These include observing Cepheid variable stars, supernovae, and patterns in the cosmic microwave background. The measurements converge within a known range, providing the basis for calculating the size of the observable universe. You notice that the observable boundary is not fixed in time. As time passes, light from more distant regions has more time to reach you. The observable sphere expands. Yet, the expansion of space also changes the calculation. Some regions recede faster than light due to expansion, not because anything locally travels that fast, but because the space between grows. This means there are regions that will never become observable, even given infinite time, because the expansion carries them away faster than light can bridge. You breathe slowly as you think about this. The horizon in cosmology is not a wall, but a limit of causal contact. It is defined by whether a signal can travel from one place to another within the time available. The boundary around a black hole is a limit of causal contact too, but in that case the limit is set by gravity. In both cases, the boundary is a consequence of spacetime geometry and the finite speed of light. You remain grounded in the evidence. The cosmic microwave background is the afterglow of the hot early universe, now cooled and stretched to microwave wavelengths. The uniformity and slight variations in this radiation have been measured with great precision by satellites, and they provide a snapshot of the universe when it was only about 380,000 years old, long before galaxies formed. The CMB marks a surface beyond which ordinary light cannot travel freely because the universe was too dense and opaque. You let your mind rest on how this surface relates to the observable limit. You cannot see beyond it using ordinary light, but you can still learn about earlier times through other signals, like neutrinos or gravitational waves, though those are far harder to detect. The fact that you can infer earlier conditions from later observations is itself evidence of a coherent physical history. You notice that the expansion of the universe also defines a horizon for what can influence you. The particle horizon is the limit of what has had time to reach you since the beginning. The cosmological event horizon is slightly different. It is the limit of what will ever be able to reach you, even in the future. Both are calculated from the expansion history of the universe and the properties of spacetime. They are derived from the equations of general relativity and the measured values of matter and energy. You remain calm as you consider that these horizons are not mystical boundaries. They are mathematical results that arise from consistent observations. When you measure the expansion rate, the density of matter and energy, and the properties of the cosmic microwave background, you can compute these limits. The numbers may be large, but the logic is straightforward. The same principles that describe falling objects and planetary motion describe the structure of the universe on the largest scales. You reflect on how the concept of horizon connects different scales. A black hole's boundary is measured in kilometers, and it is defined by the mass and rotation of the object. The observable universe's horizon is measured in billions of light-years and is defined by the age of the universe and the expansion of space. Yet both arise from the same underlying structure of spacetime. In each case, the boundary marks where information can no longer travel to the observer. You let your thoughts slow as you realize that horizons are not limitations imposed by imagination. They are natural consequences of the physical constants that govern the universe. The speed of light, the curvature of spacetime, and the expansion of space set the stage. You are not left with uncertainty, but with a precise map of what can be observed and what remains beyond reach. You rest with the quiet awareness that the universe is both vast and measurable. The horizon does not shrink the universe. It defines the limits of what can be known from your position. Yet even within those limits, the amount of information is enormous, and each observation adds to the understanding of the cosmos. The same physics that governs the boundary of a black hole also governs the boundary of the observable universe, and the connection is a reminder that nature's rules remain consistent across scales. You begin by letting your mind settle on a simple truth. Boundaries in nature do not imply failure or mystery. They simply mark where the rules of physics change how information can travel. The event horizon is one such boundary. It is not a wall you can touch. It is a limit defined by the curvature of spacetime and the speed of light. When gravity becomes strong enough, it shapes the paths of light and matter so that escape becomes impossible. You breathe slowly, noticing that the event horizon is not a magical barrier, but a geometric one. It is described by the same equations that predict the motion of planets and the bending of light around the sun. The mathematics that explains the orbit of Earth also predicts the existence of a boundary where light can no longer escape. This is not a leap of imagination. It is the consequence of applying tested theories to extreme conditions. You reflect on how this boundary is defined. For a non-rotating black hole, the radius of the event horizon is directly proportional to its mass. This is a measurable relationship. If you know the mass, you know the size of the boundary. This is why black holes, despite their name, are not defined by darkness alone but by mass and gravity. The boundary is where escape velocity equals the speed of light. Beyond it, the geometry of spacetime directs all paths inward. You remain calm as you think about the role of observation. Black holes are not simply theoretical. Their presence is inferred through effects that are measured with great precision. The motion of stars near the center of galaxies, the radiation from hot gas falling inward, and the shadows captured by radio telescopes all confirm the predictions. Each observation is a piece of evidence that aligns with the same theoretical framework. The consistency is not accidental. It is a sign that the model accurately describes reality. You consider how this understanding changes your perception. The event horizon is not a mysterious object that appears out of nowhere. It is a boundary that emerges when mass is concentrated enough to curve spacetime strongly. The laws of gravity apply everywhere, from the gentle pull that keeps you grounded to the extreme pull near a black hole. The event horizon is simply the limit where those laws lead to a specific consequence. No outward path for light. You let your thoughts rest on the fact that boundaries are common in physics. The speed of light sets a limit on how fast information can travel. The age of the universe sets a limit on how far you can see. The event horizon sets a limit on what can be observed from inside. Each limit is measurable and predictable. They are not signs of ignorance, but signs of the universe's structure. You notice that the event horizon also teaches a deeper lesson about observation. It shows that the universe is not defined solely by what can be seen. It is defined by what can be measured and inferred. Even when light cannot escape, the effects of gravity can be measured outside. This is a reminder that science does not require direct sight. It relies on evidence and consistency. You can understand something even when it is hidden, by studying how it influences the world around it. You reflect on the calm certainty that comes from this approach. You do not need to imagine what happens inside the boundary to appreciate the significance of the event horizon. You only need to understand how spacetime behaves. The geometry tells the story. The mathematics is not a mystery. It is a language that describes the universe with precision. You remain aware that the event horizon is not a place of drama. It is a quiet boundary defined by natural laws. There is no emotion in the physics, no intention. The black hole does not want anything. It simply follows the rules that govern mass, energy, and spacetime. This is comforting in its own way. It means the universe is not capricious. It is consistent. You think about how this boundary affects time and perception. From an outside perspective, objects approaching the event horizon appear to slow down and fade, due to gravitational time dilation and redshift. This is not an illusion but a measurable effect of spacetime curvature. The light that reaches you carries information about the changing rate of time near the boundary. The physics is precise, and it matches observations of strong gravitational fields. You stay grounded in the fact that these effects are predicted by general relativity, which has been confirmed by countless experiments. The bending of light around the sun, the timing of signals from satellites, and the detection of gravitational waves all support the same theory. The event horizon is therefore not an isolated prediction. It is part of a network of confirmed physics. This makes it more reliable, not less. You allow yourself to feel a quiet respect for the human ability to understand such extreme conditions. You consider how, through careful measurement and reasoning, humans have learned to describe objects that cannot be seen directly. The event horizon is a boundary that exists because the universe is measurable. The laws that describe it are grounded in observation. This is a testament to the power of science, not a sign of mystery. You notice how the boundary connects to the larger universe. The same principles that define an event horizon around a black hole also define horizons in cosmology. The observable universe is limited by the speed of light and the age of the cosmos. In both cases, the horizon is a consequence of spacetime and the finite speed of information. The universe is full of boundaries, and each one is a reminder of the structure of reality. You rest with the understanding that the event horizon does not limit curiosity. It guides it. The boundary defines where observation ends, and that prompts deeper questions about how nature behaves in extreme conditions. These questions drive research and discovery. They are not signs of failure but signs of progress. Each new measurement brings the universe into clearer focus. You let your mind slow, focusing on the gentle order of the cosmos. The event horizon is not a dramatic curtain. It is a quiet line drawn by gravity and the speed of light. It marks a boundary where the rules of spacetime produce a measurable outcome. It is a natural consequence of the same physics that shapes your everyday life. You close with a calm certainty. The universe is not a place of unknowable mysteries, but a place of consistent laws that reveal themselves through observation. The event horizon is one of those laws made visible by its effects. And as your thoughts drift into rest, you carry the quiet knowledge that the cosmos remains orderly, measurable, and deeply understandable, even at its most extreme edge.